Hello and welcome back, fellow astronomy enthusiasts. We're beginning week 4 of online instruction. Hope everyone is safe and healthy and still practicing social distancing. We are making our way through this. Hopefully we'll be out of it shortly. Let's do a quick astronomy picture of the day. It is a particularly appropriate astronomy picture of the day. So again, foreground and background images. The foreground image is of a scene in Death Valley, which is interesting because totally flat landscape, nothing around, dry lake bed, easy to understand how this is formed. And in the middle of it, you can see one in the foreground, these rather large rocks. How did they get there? Well, you can read the caption if you really want to know. But more interesting is the background, which is a very nice image of this, which is extraordinarily appropriate because this is what we're talking about eventually in today's lecture. This is the disk of our own Milky Way galaxy. So more on that later. Let's do a quick review question. Here's today's review question. What is the Schwarzschild radius of a 6 solar mass black hole? You can pause your video, do it on your own, and then come back and we'll solve the problem together. All right, welcome back. I'm at home again, by the way. Got pretty much the same setup here as I do at work. Nice little whiteboard here. So let's solve this problem together. The Schwarzschild radius of a 6 solar mass black hole. Again, remember there's two versions of the Schwarzschild radius formula. There is this one, R equals GM over C squared. That is the general version. This will work for any units. You just need, well, it won't work for any units because G and C have particular units, but you use R in meters and M in kilograms, and this one works out nicely. But in this case, our mass is 6 solar masses. And if we have solar masses, then we can use the simplified version of the Schwarzschild radius formula, which is just R equals 3M. I usually put a prime there to indicate that this is the special version. But this version, remember, R is in kilometers and M is in solar masses. And that's exactly what we have here. Plug in solar masses, get out kilometers. So R is 3 times 6, or 18. And the unit, again, this is one of those formulas you just have to know, plug in solar masses, get out kilometers, so it is kilometers. This 3, if you like to do this unit stuff, has units of kilometers per solar mass, which is really G over C squared. If you do the conversion from kilograms and meters and seconds, that comes out to 3 kilometers per solar mass. And so that's how this equation actually works. Okay, great. That was recap of last week's stuff. Let's continue with our discussion a little bit of solar black holes, that is, and finish up with thinking about a way that they have been observed recently that had never been done before. And this is a very cool science story, but we have to understand another form of radiation, and that's gravitational waves. So gravitational waves are very similar to light waves. We've seen that waves have light has a wave-like property. And what emits light? Well, it turns out what emits light is when electric charge vibrates back and forth. When that charge vibrates back and forth, that change in basically the acceleration of that charge is enough to produce a photon. And pretty much any time you're accelerating charge like that, you get a photon. Well, there's an equivalent when you accelerate masses. Instead of a photon or a stream of waves, of light waves coming out of a particle, if you accelerate a mass, you generate gravitational waves. Now, where are masses accelerated? All over the place. They're accelerated when I drop a pencil. They're accelerated when the moon is going around the Earth and the Earth is going around the sun. These are all emitting gravitational waves. The gravitational waves are so weak of those things, though, that they are impossible for us to detect anyway. So how would you think about going about detecting one of these gravitational waves? Good question. What happens to matter as a gravitational wave goes by? Well, this is an exaggerated view of, let's say you had a perfectly uniform circle of masses out in space. If a gravitational wave goes by, in this case, it's propagating out of the screen. This is what it will do to the masses that are in its path, right? So instead of, causing electric charge to oscillate, which is both how it's emitted and how it's absorbed, in this case, it causes these relative positions of these masses to change. That's what a gravitational wave will do. So if we want to detect gravitational waves, we need to have something that can very accurately measure the distances, say, between two massive objects. And that is exactly how we have gone about trying to do this. This was an experiment that has decades in the making. This facility was built on something like 20 years ago. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. And this is the Hanford, Washington. This is the one in Washington State. And what they did was they built a building here, and they built two very long arms, right? You can see one of them going out all the way to the end here, and the other one is equally far in this direction. And what happens is there is a very large mass in the building. There are two of them actually, one at each end of the arms, and there's a third one at the end of this arm, and there's a fourth one all the way at the end of the other arm. And all it's doing is trying to measure the relative dispositions of those two objects. Now, how are they going about doing this? Well, they have completely evacuated this entire arm, this entire tube here, and it's bigger than it looks. And they built it. This is the largest, I think, vacuum chamber in the world, and it's 4 kilometers from the building to this outpost, and it's 4 kilometers from the building to the other outpost as well. And to give you some perspective, a gravitational wave going by, obviously the Earth and the Moon system isn't producing anything near enough. The Earth and the Sun isn't producing anything near enough. Even an extraordinarily large event that it produces a very large gravitational wave is going to move this very large mass relative to this very large mass by something like the width of an atom in difference. And so that's what you're trying to measure. Even over this 4 kilometer range and this 4 kilometer range, you're trying to measure the difference in the positions of those hanging masses by something like a fraction of an atom width. It's an extraordinarily hard measurement to make. And they were pretty sure they wouldn't find anything when they first did it, but they spent 20 years not only building this thing, well, they built it in much less time than that, but refining the techniques and getting rid of the main source of noise, which is, even a truck driving by on a nearby road makes vibrations that's causing all this stuff to shake. And so getting rid of all those vibrations is a very important part of this process. Here's a schematic showing what this actually looks like. Again, a single laser beam through a beam splitter. What does a beam splitter do? Well, it just sends half of it in this direction, and it's sort of like a half silvered mirror. Half of it can go through and half of it actually gets reflected in this direction. Now, so it actually passes through this test mass and through this test mass, And this is a 4-kilometer arm here, and this is a 4-kilometer arm here. And in a perfect world, the gravitational wave goes by, and the distances between those test masses vary just a tiny bit, and these test masses vary just a tiny bit. And if those waves come back through a process called interferometry, you can make it so that you can tell the extraordinarily small differences in position and path length that this laser has with respect to this laser. And just by measuring the amount of light you're getting here, make some measurements about the relative distance between these two test masses. It's an amazing accomplishment. Several years ago, we were finally in the position where we had made enough upgrades that we thought we had a chance to detect some real astronomical objects. And lo and behold, in January of 2016, we found some real astronomical objects. You may have heard about this. This has been in the news. This was extraordinarily important when it first happened. There have been several more since. But this is the first thing that was actually detected. What is it? Well, it's two black holes merging in together to form a single black hole, right? And so how does this work? Well, again, if you can let's look back to this thing. The bigger the gravity, the faster you can make, the more massive it is, and the faster you can make it accelerate, the more higher the amplitude the gravitational waves will be. And so what is the highest amplitude wave that's sort of possible? Well, it's two black holes, right? Because they can get very close to one another. And as they get very close to one another, as the distance between them goes down, the acceleration goes way up because the force of gravity goes way up. And as these guys are orbiting one another, now normally these guys will just be in a stable orbit and nothing really will happen. But believe it or not, just like photons carry energy away, these gravitational waves carry energy away. And that energy has to come from somewhere, and it comes from the orbital energy of these two objects. And as they get closer and closer and closer, and this gravitational wave becomes more and more intense, they'll spiral faster and faster and faster, and then they will eventually merge. And it's that final second or two before they merge, where the gravitational waves are the highest, where we have a chance to actually measure this, even though we're millions of light years away, hundreds of millions of light years away. I don't remember exactly how far away this one was, but it was a long way. So in spiral, again, this is noise. You're seeing. So they built two of them. One is in Hanford, Washington, and one of them is in Louisiana. And there's more of them that have been built now. You get more. Obviously, if you just saw a detection in one of them, you might be, well, maybe that's just noise. You can see how noisy this data is. But if you see the same signal in two of them or more of them, now you've got some confidence that you've actually got something. So here it is. There is a signal here, but I'm not sure we can detect it yet in either one of them. And then all of a sudden, look at this. You start having this synchronous oscillations. And this is showing you the amplitude of the oscillation between two of those test masses. That's not only getting more and more amplitude, but the period is going down. This is a characteristic of what we see for an in spiral event. The amplitude goes up and the period between peaks goes down as these two things spiral together. And as eventually they will merge, and then they sort of have a ring down point where the whole thing is kind of vibrating, and then it just goes quiet again. So here it is, an actual detection of a black hole merger. And they were able to determine the masses, the details that are coded in this particular in spiral, how long it takes to ramp up, what the periods are, what the amplitudes are, tells them an amazing amount. It tells them what the relative masses of each of these objects was, tells it how far away it was roughly. And so we have all of that information. And in fact, we have observed many more of these in the meantime. Here's sort of a taxonomy of the ones that have been measured. All of these blue ones are neutrons, are black holes. Actually, these are all black holes. So these are the merger events where we have, again, these are the black holes that we have discovered through these observations by these gravitational wave observatories. So here's one, for instance, where we had 20 solar mass black hole and a 30 solar mass black hole combining to make something like a 50 solar mass black hole. And you can see how these have been detected. All of these blue ones are the LIGO Virgo black holes. These are the ones where we've been detected them by merger events. These purple ones are the ones that we have detected by electromagnetic radiation. In other words, inspiraling normal matter that's emitting lots of photons. And we've even discovered now a neutron star merger, which may have created a black hole or not. We're not even really sure. So this is interesting. These are sort of a taxonomy of the known black holes that exist, sort of in order of how massive they are. Okay, that ends our study of black holes. We will move on to chapter 25 in the next video, which is the Milky Way galaxy. See you there.